In this segment, we're going to talk about solving for indeterminate systems using moment area, conjugate beam, virtual work, and Castigliano's theorem. Some important things to note. Number one, the indeterminacy of the beam is by 1 degree. Number two, we need to remember our boundary conditions. So that, for example, is at a pen and a roller, vertical and or horizontal deviation is 0. At a fixed end, slope and deviation are 0. Let's say we have this propped cantilever with a fixed end at B and a roller at A, and we want to find the reactions at A in terms of the moment load M and the length L using moment area method. First, let's write out my reactions. I have a reaction AY, and then I have a reaction BY, BX, and the moment at B. I have 4 reactions and 1 member, which means I am indeterminate by 1 degree. My moment load is going to cause the elastic curve to bend down here and then come back up to flat at the fixed end. Remember, a fixed end does not allow slope or deflection, so that means there's no rotation and no translation. So it should be flat and the same ending point as it is starting point. A, however, allows rotation, so there is a slope at A, but it does have no vertical deviation. To use moment area method after the elastic curve, the next thing that we need is moment diagram by superposition. With moment area method, the nice thing about the theorems is there is 0 slope at B. So if I draw a tangent line at B, then right here, my distance between my point A and a tangent line drawn at B is equal to 0. And that is the boundary condition and the second theorem of moment area method that I'm going to use to solve for my reactions. Theorem 2 is taking the moment diagram and summing the moments about a point. So because I am looking at point A on my elastic curve, that is the place that I want to sum the moments about. So starting with the moment diagram, I'm going to have base of length, height of M, and the distance to its centroid from A, length divided by 2. And that'll be going counterclockwise, so I'm going to add it to my equation, as is my AY reaction. So it is 1/2 base times height times the distance to its centroid from A, which is 2/3 the length. And this is all equal to 0. So solving for AY, I find that it is equal to 3M divided by 2L, and I get a negative answer, so it is actually acting down. Now that I have that one reaction solved for, I can use equilibrium to solve for the other reactions. Summing forces in the y direction, I have minus 3m over 2l plus by. Solving for forces in the x direction, I get bx, and last, summing for the moments about B, I have the moment at B minus the moment load plus AY times length L, and I find that the moment reaction at B is equal to M divided by 2. I get a negative answer, so it is actually acting clockwise. Here we have a beam that's supported with a pin at B and then rollers at A and C. I have a distributed load of 4 kilonewtons per meter, and I want to find the reactions at A, B, and C using conjugate beam method. Again, the system is indeterminate because I have one reaction at A, 2 reactions at B, and 1 reaction at C. 4 reactions and 1 beam, so we are again indeterminate by 1 degree. We can't solve this with equilibrium equations to start out with. So I'm going to start with conjugate beam. With conjugate beam method, the first thing that we need is moment diagram by parts. Now we need to draw our conjugate beam with the moment diagram loads. So A is a roller, which means that it allows for slope, as does C. And B is a midspan pin, so we need to represent that on our conjugate beam with a hinge. And then I apply my loads. I have on my conjugate beam 1, 2, 3, 4 unknowns. So I'm going to have to do a little bit of work here to get some answers. I'm going to start by summing moments about A. And I will have 1/2 base times height times 2/3 of base for my first triangle, and that is going counterclockwise, and then I'm going to subtract my parabolic slice here, so that is 1/3 base times height times the distance to its centroid from A. And then my last triangle. And then last, my conjugate reaction theta C. Solving for theta C, I get 10,125 over 14 minus 225 AY over 7 minus 2600 CY over 21. Okay, so I have an equation for theta C. Now I did that because I have a hinge at B, so now I can draw a free body diagram of B to C and solve for another theta C equation, set them equal, and get some answers. On my free body diagram, section BC of my conjugate beam, I'm going to sum my moments about B, and I will have 1/2 base times height times the distance to the centroid from B plus 20 theta C. And again, solving for theta C, I find that it is equal to minus 200 CY all over 3. I now have 2 equations for theta C, so I can set them equal to each other. And when I do that, I find that I still have 2 unknowns, AY and CY. So what I need is another equation that relates AY to CY. So coming all the way back here to my original given problem, I see that if I sum moments about B, I can get AY and CY isolated and one in terms of the other. I find that AY is equal to 30 plus 4/3 of CY. I'm going to take that value and plug it into my conjugate beam values. And I've finally reduced my equations down to 1 unknown. Solving for CY, I find that it is equal to 2.41 kilonewtons, and I get a negative answer, which means it is acting down. Plugging that back into my AY is equal to 30 plus 4/3 of CY. I find that AY is equal to 26.8 kilonewtons, and it ends up positive, so it's acting up. And then last, I'm going to use the original given system and sum for forces in the y direction. And I will have AY minus my load plus BY minus CY. And we find that BY is equal to 35.6 kilonewtons, and it is also acting up. And then if I sum for forces in the x direction, I find that BX is equal to 0. We have another propped cantilever where it's fixed at A and has a roller at C. This time, though, we have two different cross sections. We have two different inertias. From A to B, it's 300 inches to the fourth, and from B to C, inertia is 200 inches to the fourth. We want to find the reactions at A and C, and this time using virtual work. Again, boundary conditions. I have three different options here. I can do deflection at A or deflection at C is equal to 0, or I can do slope at A is equal to 0. I'm going to go with deflection at C is equal to 0. And that's going to equal the sum of the integrals of big M, little m, all over EI dx. And I'm going to take my x origin from C. I'm going to need two sections. I need a section between B and C where I don't have any load and I have my first inertia of 200. And then I'm going to take my second section from A to B where my inertia changes and I start a distributed load. My moment one equation is going to be CYX for section 1. For section 2, that represents 10 to 20 feet, my moment 2 is going to equal to CYX minus 4 times x minus 10 times x minus 10 divided by 2. So this cleans up to moment 2 is equal to CYX minus 2x squared plus 40x minus 200. On my virtual beam, I'm going to remove the reaction CY and replace it with my virtual load 1, because that is the deflection that I'm looking for that I know is equal to 0. So that's what I'm going to do there. I'm going to take the same sections, and what we're going to find is sections 1 and 2 on my virtual beam have the same free body diagram. So my virtual moment 1 is going to equal to my virtual moment 2, which is going to equal to x. And I can do this because I have my moment with compression in the top on my virtual beam, and on both of my given beams, I have moment compression in the top. We have to make sure all the moments are acting in the same direction so we don't get any sign confusion. Now we put this into our virtual work equation. So the deflection at C is equal to 0, and it's going to equal to the integral from 0 to 10 feet of my M1 equation, CYX times my little m1 equation all over E, which is constant, I, B, C. So there's where our inertias come in, plus the integral from 10 feet to 20 feet of my big M equation, CYX, x squared And the way that I have my sections drawn from 10 to 20 feet from C, that is where the inertia AB takes over. Now remember, this is only from 10 to 20 feet, so I only have inertia AB acting on this second section. When I solve for the integrals, I see that I still have this problem of different inertias, IBC and IAB. Setting up a relationship, I have IBC is 200 inches to the fourth, and IAB is 300 inches to the fourth, meaning IBC is 2/3 the value of IAB. So I can plug that in over here, and now I have a common denominator throughout the entire system. And this now cleans up to 8,500 CY over 3 EIAB is equal to negative 35,000 divided by 3 EIAB. So my E's and I's now divide out, as do my 3's actually, and I solve for CY is equal to 4.12 kilopounds, and I do get a positive answer, which means it is acting up. Now that I have that, I can go back to my given system, and plugging in CY, I have AY is equal to 35.9 kilopounds up. Summing for the forces in the x direction, I have AX is equal to 0. And last, summing for the moments about A. And I find the moment reaction at A is 118 kip feet and 3 significant digits. And I get a positive answer, which means it is acting counterclockwise, which is the same as my assumed direction. For our next example, let's change it up and have a frame. This frame is pinned at A and pinned at C. So I'm going to have reactions AX, AY, CX, and CY. 4 reactions, 1 member, so this is indeterminate by 1 degree. We want to find the reactions at A and C, and we want to use Castigliano's theorem. So with Castigliano's theorem, we add a point load P or an applied moment P, depending on if we want to find deflection or slope, respectively. Since I have pins here, deflection is what I want to find because my boundary condition is that pins are not going to allow deviation horizontally or vertically. Just for kicks, what I'm going to do is replace CX with my reaction P, which means that the Castigliano's theorem I'm going to use is the horizontal deviation of C is equal to 0. And that's going to equal to the sum of the integrals of the moment, the partial moments with respect to P, all over EI dx. To get my moment equations, I need to make sections. So I've got C to B. That's going to be my first section, and I'm going to take it to the right towards C. And then I have a corner at B where I travel down to my 80 kilonewton force. I am again going to take my section towards C because that is going to limit me to the one reaction CY that I don't know in terms of P instead of dealing with AX, AY, and C. Same goes for section 3 between the load and pin A. Since I'm taking everything towards C, I'm going to sum my moments about A to get CY in terms of P. And I get CY to equal 160 plus 4P divided by 3. I'm going to set up my origin X taken to the left from C and my origin Y taken from B down. For section 1, my moment 1 equation is going to be 160 plus 4P divided by 3 times the distance X. And if I Take the partial of moment 1 with respect to p. I get 4/3 x. P is really equal to cx. Therefore, my moment 1 equation is equal to 160x plus 4cx divided by 3. Setting up section 2, which represents the top half of my y from 0 to 4 meters. I solve for moment 2 is equal to minus py plus 160 plus 4p divided by 3 times 6. I'm going to expand this one out. And when I take the partial of my expanded m2 with respect to p, I have minus y plus 8. P is really equal to cx. Therefore, my moment 2 equation is really equal to minus cxy plus 320 plus 8cx. Section 3 goes from 4 meters down to 8 meters. We've now got that 80 kilonewton horizontal load added to our vertical portion. And summing at moments about 3, I get moment 3 equal to minus p times y plus 160 plus 4p all over 3 times 6 minus 8 times y minus 4. That's an 80. Expanding this out, moment 3 is equal to minus py plus 320 plus 8p minus 80y plus 320. Taking my partial of m3 with respect to p, I get minus y plus 8. P is really equal to cx. Therefore, my moment 3 equation is equal to minus cxy plus 640 plus 8cx minus 80y. I'm going to plug this all into my horizontal deflection at C, Castigliano's theorem equation. Solving the system set equal to 0 because I have no horizontal deviation at pin C. Pin C holds it into place. I find that Cx is equal to a negative 48.6 kilonewtons, which means it is acting to the left instead of my assumed direction to the right. Plugging that back into my Cy equation, I get Cy to equal 11.4 kilonewtons, and it also ended up negative, which means it's acting opposite of my assumed direction down. Remember when we set up our Cy equation, we assumed Cx acting to the right. So I need to make sure that that negative sign is in that equation so I get the correct directions. Next, I can use my given system to solve for Ax and Ay. And I find that Ax is 31.4 kilonewtons. It also is negative, which means it is acting to the left. Summing forces in the y direction, I get a positive Ay, which means it's the only one of my assumed directions that ended up positive. It's acting up at 11.43 kilonewtons.